Okay, I guess no one has any. Okay, no one has any questions, so far we can resume. Let's start. Okay. Right. Like I said, we just need to split this system, this whole block, I mean, this whole network into separate systems, right? So this one is separated into, I mean, the solution given here is separated into one system, then two system, and the third system, right? Over here. And the fourth system, it is this particular system over here, right? This is the fourth system. Like I had already shown you that you can break this system into multiple blocks, right? So this particular, I mean, the solution given over here is broken down into multiple blocks, and then using our substitution method, we can evaluate the final equation for the whole system. But there are other methods as well, but we'll stick to this because this is simple. We can break it down into separate blocks, and then we can substitute, right? Right. So we were at we have finished with omega, I mean Wn, right? We were at V of n. So V of n is basically equal to W of n delayed by 1 unit, right? And then we get V of n. So basically V of n is equal to Wn minus 1, right? Okay, that is what we get. We now know that Wn, right? We know that our Wn from here, we know it is a single delay of U of n, right? Now we can write V of n, right? We can rewrite V of n in terms of U of n. So basically what we do in Wn, we substitute n minus 1, right? So if we do that, we'll be going to end up with n minus 2, right? So we have now written V of n in terms of U of n. We have written W of n in terms of U of n, and we know our U of n, right? It's the first place. We can also write an equation for Y of n. So you can see this outer block gives us Y of n, isn't it? This outer region that is made up of signal Wn and V of n, right? So Y of n is equal to V of n, right? You can see from here, Y of n, right? Y of n is equal to V of n. V of n, this is the signal, the output signal, V of n minus this part. If you take this, Wn multiplied by minus 1, we are left with minus Wn, right? So it is basically this block, Y of n is equal to V of n minus W of n, right? Is that fine? Now we know that Y of n is equal to V of n minus W of n, and we know that W of n is U of n minus 1, and V of n is equal to U of n minus 2. So we can rewrite this whole formula, this part, right? We can rewrite it as, I mean, we can rewrite it using U of n, right? Because we know that W of n is this, V of n is this, right? So rewriting Y of n in terms of U of n, we are left with this, right? Okay. Now what we need to do, we can directly substitute U of n with the value over here, right? In terms of X of n. We can write Y of n in terms of X of n. So basically what you need to do in U of n, you just need to delay the system by 2 units and minus it by U of n delayed by 1 unit, right? So evaluating that, you should be getting this. Is that okay? I guess everyone can evaluate that, right? It's just basically rewriting, substituting this and rewriting. I know it's a bit confusing, but the theory behind this is just to break these blocks into separate blocks and rewrite it, right? You write it down in different signals, and then based on that, you try to substitute, right? Substitute, keep substituting. Is that fine? Okay. So if you still have any problems, and once the uni opens, you can come back to me, right? with this. Now, I hope this one everyone can understand, right? It's pretty much clear. You can just break this down into multiple systems and rewrite it. Right? Keep rewriting it until you get in terms of the initial input signal and output signal, right? Then moving on to question number, part B of this question, we are given the following system: y of n is equal to 0.001 to the power of n, x of n. Determine whether the system is linear, shift invariant, causal, or Bibo stable. So what I have seen is that most of you guys haven't done any sort of working, but directly have evaluated that the system is linear, shift, variant, causal, all those stuff. Right? You have just directly written that. So that is where you guys lost marks, right? Actually, you need to evaluate or show some sort of working. So the first thing when you are dealing with linear system, what you need to do is to test for homogeneity and additivity, right? Isn't it? So what you do, you take this, you consider um, this function, right? And rewrite it in terms of, let's say, test is constant multiplication, right? That is scaling up x of n. So you multiply with a constant. So that would be the y1 of n, right? So that is y1 of n, right? That is what we are having over here, right? And then y2 of n is basically the same thing with multiplied with a of 2, that is another constant, x of 2, right? Then what we do is that is basically y, that is another y of n, which is equal to y1 plus y of 2, right? So basically, based on what you are learning is just taking, substituting x of n, right? This x of n, considering that x of n is a multiplication and a summation, right? Both are additive and homogeneous, right? We consider that and we expand it, right? We rewrite it. We rewrite the whole function in terms of that, right? So we have these, we rewrite that, right? We have in place of x of n, we are just directly substituting with this term, right? This is just a test for homogeneity and additivity, right? Once we have that, we directly substitute it and we can see that the outer constant could be multiplied into this, right? So expanding then that will have this part and this part, right? Like I said, if we had to earlier rewrite this, we could have reconsidered this as y of 1, and we could have considered this as y of 2, right? So if we have two of these, and we have considered that y of n is a summation of y1 plus y of 2, then it is linear, right, in that particular case. So in order to test this, what we just needed to do is to substitute a1 of x of 1 and a2 of x of 2 into the actual formula, right? This actual formula, and test whether we are getting y1, this particular part, and y2, this particular part. If we are getting that, right, we can see it is a function of 2, right? We are getting this, so it is linear in this particular case, right? Is that fine? I believe you can use your old 2 to 4 theory. This is what I'm just saying is just the 2 to 4 theory that you guys are familiar with, I guess. All of you know that? All of you know how to determine how a system is linear or non-linear? Okay, you guys actually need to recap on this, right? This is a bit complicated part, but what I suggest is use the older method that you guys have learned in what do you say, in your 2 to 4. But if I have to quickly recap on that, it is, we just consider this same function, and then if it is what do you say, homogeneous or scalable, right? It is you can multiply any variable. So we consider y1, right? Y1 to be equal to a1 y of n, right? And y of 2 is equal to y of, right? This is multiplication part, right? So if it is linear, what happens is you should be ending up with y of n is the summation of both y1 and y2. Okay, you get that much, right? I believe this is simple. Now what you actually need to do, if y1 plus y2 are additive, that means your input x1 and x2 could also be additive. You can add those, isn't it? So y1 is equal to basically a1, right? a1 multiplied by this term, and y2 is equal to a2 multiplied by this particular term over here, that is 0.001 to the power of n x to the power, x of n, right? So you have these two functions. Now you just need to test whether it is a summation of that. If you substitute a1, in place of x of n, we substitute a1 multiplied by x of n plus a2 of x of 2 of n, right? That is what we are getting, and we should get y1 plus y2 at the end. If it's linear, your input additivity and homogeneity should equal to your output addition, additivity and homogeneity, right? So we have considered that when we are considering y1 and y2, we have considered that y of n is basically, if it's homogeneous and additive, y of n is equal to y1 plus y2. This is one condition, right? We are just multiplying with a constant and adding y of n. Then we have to just test with the x of n as well. We can consider x of n equal to the same property, that is equal to x1 plus x2, and both x1 and x2 are the same multiple of this constant. If it's linear, your input varies by the same constant as your output, right? If it's linear, that is what is being done over here. You have considered these two, and then you test for your x1 and x2 replaced in place of x of n. So doing that, right, replacing x of n, which is a additive and homogeneity property, right, that is x1 plus x2 multiplied by a constant. Replacing this into this particular formula, we should be ending up with y1 plus y2, right? Expanding this, we can see that this particular part, as assumed earlier, was our y1, and this particular part over here is equal to y of 2. So since y of n is equal to y1 plus y2, it is linear, right? Again, if you have missed, if you don't get this, just recap on your old notes, right? Then moving on to the second part, is it shift invariant? How do you determine if it's shift invariant? A shift in your input should result into the same shift into your output, right? Isn't it? If a system is shift invariant, a shift in input results into a shift into output, right? So we do that, right? We introduce a shift into our input and test whether we are getting the same shift in your output, right? Over here, if we introduce a shift into our x of n, right? By m units, we can see, right? We are replacing basically. We get this particular part, right? If we're introducing a shift in our output, right? This is what we get. If we introduce a shift in our input, right? Pardon me. If we introduce a shift of m units into our input, the whole formula, right, will be rewritten as this, right? That is 0.001 of t x of t minus 1. This is what we get as our output, right? But if we introduce a shift in our output, basically the whole formula can be rewritten as 0.001 t minus m x of t minus m, right? We can see both of these are not equal, isn't it? When we introduce a shift in our input, we get a different value. When we introduce a shift in our output, we get a different value. If both the values are different, that means our system is shift varied, right? Then the second part, that is whether the system is causal or not. So just by observing, we can see that the system is causal, right? Because the inputs are not dependent on the future inputs, right? It's just dependent on the present. Sorry, based on this formula, it is just dependent on the present input. Whether the system is Bibo stable or not, right? What we do is we introduce the stability. When there is a bounded input, there should be a bounded output. So in this particular case, if we bound the input, we bound the output, we get this, right? That means we are bounding the input, right, in this particular case. So we can see if we bound the input, the system is not stable. If we bound the input, we can see that this particular part approaches to 0.01, approaching to positive infinity. It is bounded, right? It approaches to 0, right? While going towards negative infinity, it is not bounded, right? It will be just growing without any bound. While the negative towards the positive side, it is bounded by 0. So based on that, since it is diverging, the system is stable. Problem number 3. Given the following sequence, this is the x of n. For n is equal to the values are given over there. Find the corresponding discrete time Fourier transform. So, okay, most of you, what you did, you have taken this sequence, and you have utilized it in A, right, in your exam paper. Or some of you have utilized this sequence and computed both A and C, right? That is one of the mistakes you can see. Your x of n is different, your y of n is different. You need to compute dTFT for x of n, while you need to compute a TFT for y of n. So the formula for dTFT, right, just seeing this, it is a continuous, what do you say? It is a continuous discrete signal, right? It is not, it is an infinite series, right? It is an infinite series. It continues towards your positive side, it continues towards your negative side. So if the system is in infinite series, we compute the DFT by this particular formula of here. X omega is equal to summation of x of n multiplied by e to the power of minus j omega n from negative infinity to infinity, right? This is the formula for discrete Fourier transform, right? Discrete time Fourier transform, right? So it was simple. Just take these values, right, and substitute it into the formula, and you should be getting this. Okay, it was very simple for the first part. For B, plot the magnitude and the phase factor. What you needed to do was to actually to draw the phase. It was phase of these, right, plus phase of these plus the phase of these, isn't it? In this particular case, you can see all are real values, right? All are real values. There's no imaginary values in this particular part. So phase is 0 directly, right? All these values are real values. There's no j introduced in this particular case, or we are not using e to the power of j theta. So basically, the phase of real value is 0, isn't it? We just throw a 0, and then what we do, we just find the magnitude of this. That's when omega is equal to 0. We substitute in place of 0, right? And we get 6 plus 4 plus 2, that is equal to 12. That is the magnitude over here. And then likewise, we substitute different omega values, that is 0.255 to 0.255, and see what is the values of these three terms, and we add it up, and we move on to the other 5 values, and this is what we should be getting, right? When we plot the magnitude plot of this, right? Is that fine? This was simple, right? Oh, and the other thing is to identify which point is this one, right? This one. So it clearly says your first point is -5, right? In this particular case. So this point is your -5 point. This point was -4. This was your -3, -2, -1. And this point was your 0 point, right? So when you are identifying x of n, so when it says x of 0, so your value was 0 in this particular case. When you substituted n is equal to -1, you needed to use this particular point over here, that is 1, right? And like forth, right? You need to reflect this n values. It has been already stated over here, so you just needed to reflect it on the x of n part. So let me just show you how we get this particular first part. So you can see our actual value starts from this particular part, it's 3, right? So 3 is at point -3, right? So x of n when n is equal to -3, right? X when n is equal to -3, x of n minus 3 is 3. So this is what we get, 3 multiplied by e to the power of minus j omega n is -3, right? So this is how we get this particular term. So likewise for second part, -2 when n is equal to -2, the value is 2, right? X of -2 is 2, e to the power of minus j omega, and our n value is -2. So this is how you substitute, right? And this is how you get the get this particular term, right? And then use our trigonometric properties to get to this part, get to these cosine parts, right? You can see that 3e to the power of minus omega of -3 and 3e to the power of minus j omega could be regrouped, right? Regrouping it will give me 6 4s of 3 pi using our trigonometric rules, right? Okay. Then we needed to then moving on to the second part, we needed to we have already drawn the plot, plotted the magnitude and the phase spectra. So for part C, we needed to determine the 5-point discrete Fourier transform of the following sequence. So the term itself, discrete Fourier transform and discrete time Fourier transform, right? Discrete time Fourier transform is continuous in frequency domain, right? Discrete time, it is discrete in time domain, but in frequency domain, it is continuous, right? You can see just by the formula, it is given by that x of omega, right? It is continuous, it is not discrete. But the term discrete Fourier transform, DFT, indicates discrete Fourier transform. That means the Fourier transform is discretized, isn't it? Okay, so that means when we are discretizing, what happens? This omega changes into 2 pi upon capital N multiplied by k. We are dependent on the discrete value that is defined by k, right? So it is given by x of k is equal to sum of n is equal to 0 till n minus 1, right? Capital N minus 1, x of n e to the power of minus j 2 pi k whole thing upon capital N multiplied by n. So we are just finding the discrete Fourier of it, right? This is the formula that we needed to use. Always remember the difference between DTFT and DFT is that DTFT, it is for a infinite series. For a DFT, it is a definite series. Okay. So this is limited, isn't it? It is not continuous towards the positive side, or neither it is continuous towards the positive side, right? Neither continuous on the positive or the negative side. So it is a definite series, isn't it? While this one is continuous, it continues towards your positive side and it continues towards your negative side. So DTFT is for a continuous series, right? It is indefinite series. DFT is for a definite series, right? And then DFT is discrete in frequency domain, while DTFT is continuous in your frequency domain. So that is the difference between DTFT and DFT, right? So just using the formula again, you just needed to substitute the value, and this time y of n is given over here. We can see our capital N in this particular case would be the number of points in that definite series. So that is 1, 2, 3, 4, 5. Right? So capital N is 5, right? K is the value that is what we are identifying, that discretizes the whole frequency domain, right? And yeah, that's all we needed to substitute. So then, oh, and n minus 1. So like I said, our capital N is 5. So the limit, the upper limit is capital N minus 1. So 5 minus 1. So we are left with 4, right? So we have this simplified, just directly substituting our capital N into this main, into the DFT formula, right? And then the rest is just directly substitution. When k is equal to 0, when you substitute k is equal to 0, what happens? If k is equal to 0, so the whole sequence, right? The whole sequence is just the addition of all the terms, isn't it? So we are just left with x of n multiplied by e to the power of j 2 pi upon 5 0 n. So this particular term e to the power of minus, right? This whole term turns into 1, right? Isn't it? This whole term gives us 1. So we are just summing up x of n. So we just needed to sum this -1 plus 1 plus 5 plus -1 plus 1. So we are left with just 5, isn't it? Because this -1 and this 1 cancels off, right? So yeah, this -1 cancels off with this 1. So we are just left with the summation of 5. So x of 0 is equal to 5. Then we needed to check for the rest of the points. X is equal to 1. Likewise, we substitute all the values, we sum it up, and we substitute in place of k, we substitute 1, right? And this is what we get. So likewise, you do it, okay? X to the power of, x of n minus 1. It will give me this whole sequence, right? Is there any question? Like, is this fine? You get how we get this particular part, right? In this question, n is equal to 5. If it was not stated, then what do we get? Okay. In this particular case, it was stated, right? If n wasn't stated, what you just need to do when we are computing a DTFT, we just need to count the number of points. So that is 1, 2, 3, 4, 5. So that becomes our capital N, right? Is that fine? That's how you determine our N. If it's not stated, the number of points in the series is our N, the capital N. Is that fine? Then for problem number 4, find the impulse response h of n of digital filter amplifier with frequency response of h of omega. So again, in this particular case, we need to find h of n. Like I said, it is direct substitution into the formula, isn't it? H of n is equal to 1 upon 2 pi. Right? Going back to the table, if you want to use the table, that is fine, because it does not matter, because we already have a frequency response. We just need to work back to our h of n. So in time domain, it is continuous. frequency domain, it is continuous. In time domain, it is discrete, right? So we just need to identify that particular part, and this is what we get. This is the particular formula that we have, and we just needed to integrate. We just needed to integrate from negative 3 pi upon 4 till pi, negative pi upon 4, right? Negative 3 pi upon 4 till negative pi upon 4. So this is the integration of this particular portion, and then this particular term gives the integration of this particular part, right? And this is just the integration of h omega is 2, right? This is just a constant 2. The constant 2 should have been here rather than here, right? But they have just simplified in this particular solution, right? They have just factored 2 outside these particular terms. So that's how they get 2 outside, right? And simplifying using our trigonometric properties, we just end up with 2 sine 3 pi upon 4 n holding upon n pi. Even if you had stopped up till done some parts of this integration, and you have left it in terms of e to the power of j omega n, that would have been still fine, right? Because integration of e to the power of j omega n is just division of e to the power of j omega n by the derivative of j omega n, isn't it, in terms of omega. So we are ending up with division of j omega in this particular case. Sorry, jm. Okay. So let me just quickly take your attendance. We have just left with 7 minutes. Okay, all right. Okay, actually, this would have been a lengthy paper. Actually, it's not fit for a 50-minute paper, right? Unless until if you had known the whole concept. Like I said, it was slightly difficult for me as well. I might have not finished in 1 hour, but I would have done enough to at least get a 7 or 8, right? I've taken your attendance. Actually. Unfortunately, that's not up to me to give a short test or not. That is up to your lecturer, right? But I'll send out the expanded solution for the convolution part. However, I want you guys to try out the other parts. That is for question number, like for this part, question number 4. That was simple. You could have got it right if you had written some sort of at least in the equations. You could have got some marks, right? Question number 3 was also easy, somewhat easy, at least for part A and B. Even if you had just written this phase is equal to 0, you would have got some marks. This was also simple. This part B of question number 2. I guess part 2A, it would have taken you a little bit of time, but the rest you should have been able to do. For question number 1 and 2, at least you should have got it. Anyway, I'll pass on the whole actual solution for question number 2A. 1B to you guys, right? How do we compute the conjugation? So unfortunately, I don't have that writing materials of here that I can explain it. The highest mark is actually 5. I think it's 5, the borderline. And that is only one of the students, right? Okay, but that's all for this remedial class. Nick, what do you want to learn in this remedial class? Anyone has any ideas? You can turn on your speakers. Actually, you need to speak, just turn on your speakers. You have 3 minutes. Five or eight. What is 5 or 8? Oh, highest mark is just 5, by the way. Highest mark is just 5. Please pardon me with the explanation of the linear part because I don't have the actual tools to actually to explain you how to determine whether it's linear or not. But I should have actually brought the notes for that particular part. But in book, it also uses the same particular part. So what I have to use with the four notes. Anyways, so that's it for this remedial session. I'll email you guys the solutions, right? So we'll end the session over here.